Hello everyone, this is Mr. 13 Things, or Silence Did Good, depending on which page I'm sticking this out onto. And we're here today to talk a little bit about, once again, my obsession with and why with the concept of the lattice method. But this time we're going to tie it into something called Taylor series. Kind of play around with this a little bit. And the idea of Taylor series and the idea of why we do a lot of polynomial multiplication. Polynomial multiplication. If you remember, just to do a quick review, what they traditionally teach as the lattice method in everyday math and a lot of other places, also known as Napier's bones, has to do with the concept of number place, or the concept of if you're going to multiply, for instance, do one here, 53 by 42, there is a pretty interesting and fun way to go about, to go about dividing and thinking about place value, that if you multiply this case 2 times 3 is going to be equal to 6, and it actually means 0 in the tens and 6 in the ones. This 4 times 3 actually means 40 times 3, which is going to be 4 times 3 is 12, which is actually 120, which is 1 in the hundreds and 2 in the tens. And if you notice here, the 2 and the 0 are together, so that's going to end up giving a value down here. 2 times 5 is actually not 2 times 5, it's 2 times 50. But 2 times 5 looks like 10, but that's actually 1 in the hundreds and 0 in the tens. And then the end, 4 times 5 is actually not 4 times 5, it's 40 by 50. 4 times 5 is 20, but actually that is 2 in the thousands and 0 in the hundreds. By the time you then add up along the diagonals, you get a 6 here, you get a 2 here, you get a 2 here, and you get a 2 here by adding down. I'm going to check again, 6, which is the 2 times 3 is 6, and then the 2's come down. These turn out to be 2, and so the answer that becomes 2,226. That's based on the concept of place value. But it includes in that this whole weirdness of the diagonal sliding and whatever else. So, but the format in and of itself is really tied to something that means you can take any number and divide it up into a bunch of other numbers and then multiply each number by the other number, and to get the answer, that's we're going to put out to vi heart. So vi heart really tells us what we're doing. And now we're going to go back to the Taylor series here. So if you want to look at the lattice method, you can find a lot of people on different ends of it. It turns out not the inability to draw straight lines is one of the big deals. So now I'm going to actually take out right now, and I'm using a triangle on top of a Wacom tablet right now. I've got to establish where my thing is. I'm actually taking out right now, and I'm going to putting a triangle on top of a Wacom tablet, so I can draw some straight lines, right? Look at that. Oh, guess I got to slide it down a little bit. Takes a little bit of a while to figure out what you're going, but I'm going to go ahead and draw some straight lines here. All right, so, and we're going to now think essentially about how this looks in another way, shape, or format. So I don't have sliding triangles, so I'm going to do my best to establish that I've got a parallel line here, and I'm sliding down. I'm going to go ahead and kind of do another lighter line here, and we're going to just multiply, and I'm going to do this one freehand. I'm going to multiply, and you can see the difference between freehand. And in this, you see one of the biggest issues, I guess, with a great program called Smooth Draws. It doesn't have the ability to draw a straight line. So if someone could write a little addition to that, that would be great. Now, what we're going to talk about is how we divide different numbers up, and the kind of theory of the Taylor series. And the theory of the Taylor series is that, in fact, any kind of well-behaving function can be written into something that looks like this. I'm going to do what you're not supposed to do, which is erase this out here. Edit, cut. And I'm recording this at 12 1280 by 720, though in the end, as I'm heading towards a 7-inch format here, this may be the last time we record. 1280 by 720 is a standard HD format. It's stuck out at YouTube. It really takes out some of the hassles in the processing. You kind of know where you're going. It'll scale it up and down pretty nicely on YouTube. But we're going to go and talk right now about the concept of multiplying polynomials together. And polynomials together can either be written this way. You're most likely to learn them in math class as something like this. Maybe something like 5 times x cubed plus 2 times x squared plus 3 times x plus 7. But we have to realize when we're doing that, there's an implied 7x to the 0 there. So that's a typical polynomial. When you start thinking about the Taylor expansion, the Taylor series of the same polynomial, it's actually written this way. Okay. And that's one way to think about it. It's 7 times x to the 0 plus 3 times x to the first power plus 2 times x squared plus 5 times x cubed, which exactly is the same thing. And if you look at Professor Grist's discussion of how you go about solving this or coming upon this realization, you can realize it just seems like you're using the one of the properties of mathematics, that you can kind of basically move things around when they're addition. And I can't remember offhand which commutative, maybe. Yeah, a plus b equals b. A plus b equals b plus a. So that's what you've used the commutative property. All right, so that's the concept here. So if we're going to write this polynomial, right, this is what it would look like. And usually it starts with a 0, first, second, third, fourth, and very often when you get into Taylor series, that might turn out to be something plus what's called higher order terms. And so there'll be a whole bunch more going up there. So these things, when you think about it theoretically, may go up infinite. So there's a couple different ways to think about this. One would be, if you're going to go to an infinite number of terms, you might want to start thinking about, I'm going to change color here. You might start thinking about perhaps putting the, and you're probably not going, putting the x to the 0 term here, the x to the first term here, the x to the second power there, the x to the third power there, and then the dot, dot, dot being higher order terms. In the same case, if you were actually squaring this, you would do the same thing perhaps going up. So this would be your x to the 0 term, this would be your x to the first term, etc. going down, x to the second term, x to the third term. So there would seem to be some logic in kind of radiating these polynomials or the Taylor expansions out from that point. Though in reality, habits are hard to die, so it's more likely you might do something when you're doing a Taylor expansion of doing this, going this way, and then starting and just deciding how many orders you're doing in your polynomial, and so starting x to 0, x1, x2, x3. But in this, you're going to see my point, or not, pretty quickly. We're going to multiply, we're just going to square this polynomial right now. And we're going to do that by realizing that if I take x to the 0 times x to the 0, it's going to be x to the 0. X to the 0 times x to the 1 is x to the 1. X to the 0 times x to the square, x squared is x to the second power, and this is, of course, would be x to the third power. We're putting those up there. We're going to colorize them a little bit. This is going to be an x to the first power. This is going to be an x squared, and this is going to be an x cubed, and this is going to be an x to the fourth. Right, so fourth order. So what we'll do in the end, you're going to see that there becomes, this is x to the 0 here. There is one term that's x to the 0. There are two that are x to the first power. There are two that, in this case, that are x to the second power. Two that are x to the third power, 1 times x to the fourth. And you're going to see that there's going to be this question of adding down diagonals, but without the dotted line. So let's just fill in the numbers as I change colors here. Put orange. Trying to. All right, so we're just going to put in 5. Since we're doing it on its way out, we're going to put 7 x to the 0 plus 3 x to the first plus 2 x squared plus 5x cubed. And going down the other way, I'm going to just do the first two degrees of this polynomial. So this would be 7. I'm sorry, I did this. It's going to be 7x to the 0 plus 3x to the first. And of course, then this would be 2 and 5 down here, but I'm just going to ignore those for now. We're going to remember there is no weird diagonals going on in this in terms of breaking up your boxes. And that's the problem, I think, perhaps, is when we're teaching the lattice method. We probably don't go to it where the great value is. And we're going to see later, as you try to do this by the distributive property, this visually turns out to be a lot better in some ways because you can start ignoring higher order terms. So 7 times 7 is, in fact, you notice we won't write this in a diagonal. 7 times 7 is 49. This is actually 49 times x to the 0, which is 49. 3 times 7 is 21. 7 times 2 is 14. 7 times 5 is 35. 3 times 7 is 21. 3 times 3 is 9. 3 times 2 is 6, and 3 times 5 is 15. Now you have to remember that in this case, there are things, and I'll try to now colorize them, starting at the first order. We'll do it in, let's see, red to start. So the 0 order term is there. That's the 0. So this is the 0, x to the 0 power. We'll move up the color scheme if we would, and the first order terms are here. Right? So those are first order terms. The second order terms are, up to yellow, are here. Right? Those are your second order terms. And your third order terms are here. And then in fact your single fourth order term would be there. But as you went down and filled out a more full lattice, if you would realize you'd get some patterns that kind of come down the reverse diagonal from what you saw before. Again, remember how you reversed everything here. You've radiated out from the lower order. Now, once you got into this, you're going to see what the beauty is, that you can kind of start to draw some lines on what you call, or Professor Grist calls, higher order terms. So that's why we're doing this. But now let's just see what we end up with. So in this case, we end up with, I'm going to try to go ahead and use my color sucker. See if I can pull out the color sucker there. My color, oh, that's not good. Edit, undo, that was not good. So I'm going to try to pull my color sucker here. And I'm going to put my pen back on the paper. And we know that we have 49 times x to the 0. X squared, we have 42 times x to the first, I'm sorry, those are those two. We have 23 times x squared. We have 41 times x cubed. And we have 15 so far times x to the fourth. Now, what comes up quite often when Professor Grist classes, he'll say you want a third order, basically a third order approximation. In this case, or a second order approximation, we would still need to fill in this box here, wouldn't we? Because we have the second order here, so we would go ahead and multiply that out as well. So I'll go ahead and probably poorly, 7, 3, 2. This is 2 times 7. This is 14. 14 x to the second times x to the 0. So that's going to be 14x squared. So that no longer is 23. That's 37. Point in the end here is just the reality that how bad this is designed out, but the fact that as I talk through this, I see the value in radiating out from the 0th order down when you do this lattice method. As long as you put a bunch of stars out here, you know, to keep track of that you're doing it kind of in an odd way, as long as you kind of use colors and whatever else to explain that these actually mean 5x cubed, because then what you can do is you can put a line here, right, across this, and then you can say these are all higher order terms. And in that, you get back to why, in fact, we teach kids the lattice method. We just don't tell them why we're teaching them that. Thanks for listening.